Hey guys, on the last lecture I just finished your Z transform. As earlier I have told you, in transform we have to study three types of the transform. First I discussed about Fourier transform, then I took up your Z transform, and from today I am going to start your next transform, that is a unit and module of your syllabus. That is Laplace transform. Laplace transform. Laplace transform, if you visit its history, actually a French mathematician, Pierre Laplace, used firstly this transform, and on the name of him, it's called Laplace transform. Laplace is a very good mathematician. He was a very good mathematician, and he developed also some work in probability theory, astronomy, special functions, etc. And also one interesting thing about him, that he was also professor in Paris, and he taught Napoleon Bonaparte for 1 year. And Laplace transform is actually very useful and very important application point of view, because in recent mathematics, mathematicians and scientists and engineers using this transform in engineering and science problems, because all engineering problems will be converted into the form of differential equations, ordinary differential equation, partial differential equation, and by the method of solution of differential equation, in some time there is very lengthy process and very difficult process to solve the differential equation, and by which we use the transform and we can solve. In this series, Laplace transform is also very useful tool to solve the differential equation. In this discussion, we will take first what is the Laplace transform, what are the properties of Laplace transform, and then how can you use the Laplace transform for the various functions, and then I will discuss inverse Laplace transform, and after that we come on the application of Laplace transform. Means how can you solve the given ordinary differential equation by using a Laplace transform. Okay, now I'm going to start that topic, Laplace transform. First thing, Laplace transform is a type of integral transform. In introduction of Fourier transform, I told you the Fourier transform is also a type of integral transform. Then I told you if ft is a function and we define its integral transform, then I define that integral transform is an integral from minus infinity to infinity, and there is a function k of s comma t and ft dt. Right? I told this in the introduction of Fourier transform, and I also told you here k of st is a very important function, which is known as kernel of integral transform. The kernel of transform. And all the integral transform will depend upon the various values of this kernel. And there, in case of Fourier transform, I took k of st is equal to e to power I st, you know that. Right? And also here we use value of kernel referent for Laplace transform, and then Hankel transform. Number of integral transform can be defined by this formula after taking various values of this kernel function. Here in Laplace, in case of Laplace transform, k of st e to power minus st, if we take this, then it becomes Laplace transform. So first thing you have to always in your mind, Laplace transform is a type of integral transform. Right? Now, what is the basic definition, basic formula, or first principle for Laplace transform is, if ft is a function defined for all values of t, then Laplace transform is denoted by L of ft, and this is equal to integral 0 to infinity. Limit is here 0 to infinity. Kernel of st is here e to power minus st ft dt. This is your basic formula. This is your main formula for Laplace transform. This is also known as first principle of Laplace transform. Every Laplace transform of every function can be calculated, can be found by this formula, right? And again, as I told you at that time, at time of Fourier transform, if you analyze this integral, this is a definite integral with limit 0 to infinity with respect to t. S here, S is a parameter, right? And S is always positive, number one. Number two, S may be real or complex, right? And if you see this right hand side integral, if this is a definite integral between constant limit 0 to infinity, after integration with respect to t here and substituting upper and lower limits, you will get a function of s, and we denote this function as capital Fs. So this is the basic formula of Laplace transform. If ft is a function defined all values of t, then Laplace transform of ft is equal to integral 0 to infinity e to power minus st ft dt, and after integration, after substituting upper and lower limits, finally we get in right hand side as a function of s, and we denote this capital F of s. A number of notations will be used by various books in Indian by Indian author or foreign author. If you see the book in which where somewhere it is denoted by Fs and this is denoted by small fs bar. In some question, in some books, small ft is denoted taking as capital F of t, and this will be taken as a small f of s. No problem. No problem. This is the basic formula, right? And now, what is the actually condition of existence of Laplace transform? This is the basic formula, and now from here you have a number of type of function as you studied at Laplace level, algebraic function, trigonometrical function, exponential function, and constant function. You substitute these functions here and evaluate this integral. As you know that how can you evaluate this definite integral, and then you will get different Laplace transforms for various functions. Right? Conditions, if you discuss about conditions of existence of Laplace transform at t. So there are simply two conditions for existence. Right? First, you can say the Laplace transform of ft, that is integral 0 to infinity e to power minus st ft dt, exists for s is greater than a, where a is any positive number, a positive constant. If there are two conditions satisfied, number one, ft is continuous, and number two, limit t tending to infinity e to power minus at ft exists, and this is finite. Right? Actually, these are two conditions for the existence of Laplace transform. Right? Okay, first we see whether function is continuous or not. Then we calculate the limit of this value e to power minus at into f of t. This exists and this value is finite or not. Right? But these two conditions are not necessary and sufficient conditions. These conditions are sufficient but not necessary. That is important thing. These conditions are sufficient but not necessary. Right? Means if and only if a condition does not exist here, because in somewhere function is not continuous, but Laplace transform exists. So we can say these conditions are sufficient but not necessary. For example, if we take function ft is 1 upon root t, then here it is clear that ft is 0 as ft is infinity as t tending to 0. But Laplace transform of 1 by root t exists, defined, and I will take it as a formula in coming lectures, in coming discussion. So this is very interesting, and on the basis of this fact, you can say that these conditions are sufficient but not necessary. Now, these are the basic things about Laplace transform. I told you about history of Laplace transform, who invented this, who discovered this, and then I will tell you what is the basic formula for Laplace transform. Now, come on some standard formula of Laplace transform firstly. Means we take some elementary functions and calculate the Laplace transform by the first principle, and that those becomes a standard result for your further calculation, for your further solution of the numerical examples, and we take those as standard results. It's just a result of Laplace transform. If we take first Laplace transform of 1, then we see that it is 1 upon s. You can easily verify this. By first principle, we know that Laplace transform of ft is integral 0 to infinity e to power minus st ft dt. So here ft is 1, so we take Laplace transform 1. This is 0 to infinity e to power minus st into 1 dt, and this is directly e to power minus st. Integration of e to power st is minus e to power st upon minus s, limit is 0 to infinity to 0, take 1 by s as common, e to power minus infinity, e to power 0. And you know that e to power minus infinity is 0, and this is minus 1. So finally we get the 1 by s. Now Laplace transform of 1 is 1 by s. That is an standard formula. It can be used directly in calculation to find the Laplace transform of any given function. We see that in our numerical sums, right? And by this formula, you can take Laplace transform of any constant function. For example, you can take Laplace transform of 2020, listed here. Then it becomes 2020 into 1. That is the 2020 upon s, for example. So it will cover all the Laplace transform of any constant function. Right? This is the first formula. Now, second formula, Laplace transform of t to power n is gamma n plus 1 s to power n plus 1. Algebraic function t to power n, right? So prove this again by first principle, by Laplace transform of Tn 0 to infinity e to power minus st t to power n dt. You substitute the value of ft in our first principle, means basic formula of Laplace transform. Right? First, by substitution, if you put st equal to u, then s dt equal to du. I am going to solve this definite integral by the method of substitution, right? But the limits of definite integral will remain same, because if you put t equal to 0, then you will get u equal to 0. If you take t tends to infinity, then u will also tend to infinity. So it is 0 to infinity e to power minus u, right? T means u upon s to power n, dt means du upon s. Here in integral you see that s to power n, s means s to power n plus 1, take it outside as a common 1 upon s to power n plus 1, and finally we get integral 0 to infinity e to power minus u to power n du, right? And you know that gamma function, we have already studied this in previous years. Gamma function, gamma n is defined as 0 to infinity e to power minus x, x to power n minus dx. So if you compare this integral, so simply it becomes gamma n plus 1 upon s to power n plus 1. Right? And it covers all the power function of this type. Means from here, if n is integer, then you know that gamma n plus 1 becomes in factorial function gamma n. So if n is integer, it can be factorial n upon Sn plus 1. If n is integer, this formula can be taken in this way. If n is integer, right? So from here, you can find various values of Laplace transform by putting n equal to 1, 2, 3, 4, and also rational values. Also from here, you can find Laplace. Just I discussed as a in condition as example. Here you can find the Laplace transform of under root t. Under root t, what is under root t? That is to the power half. That is gamma 3 by 2 upon s to power 3 by 2. Gamma 3 by 2, you know that 1 by 2. Gamma half is s to power 3 by 2. Means gamma half, this is under root pi upon 2 times s to power 3 by 2. This will be Laplace transform of under root t. And just also, we can find the Laplace transform of 1 upon under root t, which I took the example in the existence condition of Laplace transform. Here, if we take the function of 1 upon under root t, that function is not continuous, but Laplace transform is existing. Right? You can also find by this formula Laplace transform of 1 upon under root t. From here, if you have to find the Laplace transform of 1 by root t, means here that is Laplace transform of t to the power minus half, that is n is minus half, that is minus half plus 1 upon s to power minus half plus 1, that is gamma half amount is under root pi, and that is s to power half, that is under root pi by s, right? And that exists, that is defined function, that is finite function because s is positive. So you see here that if this function 1 upon root t is not continuous, if its value, its limit is not finite, but Laplace transform exists. And so I told you the conditions for Laplace transforms are sufficient but not necessary. Right? This was the second formula. Now, the third formula. Third formula is very simple. Laplace transform of e to power at. That is very simple. 1 upon s minus a. Where naturally s is greater than a. Right? It can be also very simply verified as Laplace transform of e to power 8 by first principal integral 0 to infinity e to power minus a t dt and so on. You know that power will be added, take minus sign as a common, then it becomes s minus t dt. Right? And integrate this simply as exponential function integration. This is this and minus s minus a upon limits infinity to 0, and then take minus s minus a as a common from the expression outside this. If you substitute upper limit, that is minus infinity because s minus a is positive, and lower limit e to the power 0. And you know that infinity is 0. So finally we get 1 upon s minus a. This is the third standard formula, third result by which you can find the Laplace transform of any exponential function by putting various values of it. If you take a equal to minus 1, then Laplace transform of e to the power minus 1 minus t. What is 1 upon s plus 1? And so on. Now, come on the next formula. That is the fourth formula, Laplace transform of sine at trigonometry. That is a upon s square plus a square. It can be also verified and proved, that is Laplace transform of sine at equal to 0 to infinity e to power minus st into sine at and dt. Now solve this integral, and this is a standard. This is a standard integral, and you have a standard formula for such type of integral. Yes, I remember this. The formula e to power ax sine bx. In case of reduction formula in class 11, 12 in integration, this is the standard formula. What is this? This is e to power ax a sine bx minus b cos bx upon a square plus b square. Similarly, there also their formula e to power x cos bx dx. This is equal to e to power x a cos bx plus b sine bx upon a square plus b square. These are two standard formula by which you can calculate such type of integral directly. In case of integrals at the class 12 level, you have studied this, you have proved this by using reduction formula, by taking this I and taking the process of integration by parts and integrate, and then you will get this. And those can be directly used here and next formula. What is by this formula? This is e to power minus st minus s sine at minus a cos at upon minus s square plus a square. Now substitute the upper and lower limits. Here again 1 upon s square, a square is outside. If you take upper limit e to power minus is 0, take lower limit e to power 0 1, but sine is 0, cos is 1, so minus a. And finally, we get a upon s square plus a square, which is your required result, right? And this is the formula for sine at of Laplace transform. And by this formula, you can find out the any Laplace transform of depending upon the sine t, sine 2t, sine 3t, and also Laplace transform of sine square t by converting into cos 2t, sine 2t by converting into sine 3t, and so on, right? This is the fourth formula, and this is the verification by this formula. These two formula are very important, and those will be used in the calculation of Laplace transform here. So let's remember these two formula, and now we take the next formula, that is the fifth result. Laplace transform of cos at is equal to s square plus a square. Right? Those can be also, I think, verified directly by this formula. No further need of proof. You can do this directly by this formula, and you will get. And this formula for Laplace transform of cos at will cover all the Laplace transforms depending upon the cosine function. Now, come on the sixth and seventh result. Sixth result, Laplace transform of hyperbolic sine at. This is a upon s square minus a square. Right? This is the Laplace transform that will cover hyperbolic sine functions. So, first of all, we see what is its verification. Again, by first principle, Laplace transform of hyperbolic sine at equal to integral 0 to infinity e to power minus s hyperbolic sine at dt. Right? For hyperbolic sine theta and hyperbolic cos theta, there is an important formula which always used to solve the integration and differentiation. As we know that hyperbolic sine theta equal to e to power theta, e to power minus theta upon 2. Hyperbolic cos theta is equal to e to power theta, e to power minus theta upon 2. These are two important formula. Always those formula used to calculate the problems depending upon the differentiation as well as integration. Right? Take this, and by this formula, open this e to power minus st, e to power at, e to power minus at upon 2 dt. Right? Take 1 by 2 outside, and then it becomes 2 integral after multiplying this, first integral e to power minus a minus t dt. Second integral, again you take integral inside the bracket. You know that by linear property of definite integral, and it becomes, if you take minus as a common, s plus a t different. Now we have two different integral, and those can be solved directly by the formula of exponential functions, right? And what is this? And now Laplace transform of hyperexponential. In right hand side 1 by 2, first integral is e to power minus s minus a into t upon s minus a, and limit infinity to 0. Second integral e to power minus s plus a t upon minus times s plus a, limit infinity to 0. Right, and now substitute the limits and solve these, and you will get your required result as minus 1 by 2. This is minus s minus a, upper limit is 0, e to power infinity, lower limit is 1. Here again s plus a, upper limit again e to power infinity 0, e to power 0, lower limit 1. Right? And now finally calculate it. Here minus 1 plus minus half, that is 1 upon s minus a. Here 3 minus, so minus 1 upon s plus a. Right? And take LCM, since then LCM is s minus a, s plus a here, s plus a, and minus s minus a. Here s is cancelled out, right? Okay, this is plus now, not minus. This is plus now, this is plus now. Right? S is cancelled, and that is plus, and finally 2a upon 2 times this is a square minus 12. This is cancelled out, and you will get your required result. That is a upon s square minus a square, and that will cover hyperbolic functions Laplace transform, right? And the sine, hyperbolic sine 2t, hyperbolic sine t, hyperbolic sine 3t, and so on. All formula, all the forms can be directly found by this formula. And now, last standard result, and that can be directly verified by yourself. That is Laplace transform of hyperbolic cos at. That is s upon s square minus a square. And I think those proof, its proof and its verification will be done very easily by using this formula and same pattern. Only you expand this after substituting this in first principle, and you will get your required result. So in first phase, these are standard results. These are Laplace transforms of some standard functions, some elementary functions, and those can be used directly anywhere, right? And this is the first phase. Now, second phase. Now I am going to start. I am taking here some properties of the Laplace transform, and that those properties can be used in the process to find out the Laplace transform of the various typical type function. Now, properties of Laplace transform. First property, what is the first property? That is linearity of Laplace transform. Linearity means if we take three functions, ft, gt, and ht are functions, all defined for t, and a, b, c are simply constants, then Laplace transform of a into ft, b into gt, c into ht. If we take such type of a linear combination, a into ft plus b into g of t minus c into h of t, then we can take as Laplace transform a times Laplace transform of ft, b times Laplace transform of gt, minus c times Laplace transform of ht. this is the statement of the linearity of Laplace transform, right? And it can be verified very easily by the simple property of definite integral for linear combination, right? So there is no need of proof. You can verify this very easily. But only you have to see and you have to follow and you have to understand what is the basic concept of this property. Actually, basic concept is that if we have a linear combination, we have a linear expression in various functions and various constants. So, and we have to calculate the Laplace transform of that expression. So, we can take it as we can take Laplace transform and inside the expression, and if there are constants and signs, so we can take the constant and sign outside the calculation of the Laplace transform. And now Laplace transform you can calculate this. So this is the property actually. Proof is not so important because proof is very easy by using the linear property of definite integral, because you know that in case of definite integral, if we can definite integral sign of integral can inside the any expression, and we can take any constant from the calculation of the definite integral. By using that concept, you can prove this. But important thing is that what is the basic significance of this property? Basic significance of this property is that the Laplace transform can be taken in any expression, and in the calculation of Laplace transform, from the calculation of Laplace transform, you can take outside any constant, any sign, and you can solve this by previous method. Okay, I am just closing this introduction of Laplace transform in this lecture, and next lecture I will continue with the properties of the Laplace transform. There are a number of properties: shifting property, change of scale property, Laplace transform of periodic function, Laplace transform of Bessel function, Laplace transform of derivative, Laplace transform of integral, and etc. In the next lecture I will discuss this, and after that I will discuss about the inverse of Laplace transform. Okay, thank you.